Oolong tea is about 1,000 molecules in total, suspended in water, but they are not all equal in importance, and one molecule in particular seems to stand out in terms of driving the beneficial health effects of oolong tea. In this video, we are exploring this hidden molecule, how it's formed during oolong tea processing, and then mostly we're going to be diving into what the scientific literature has reported about this molecule when they've used it as the subject of a variety of experiments. My name is Dylan. I am a PhD tea scientist. I research tea. If you're into tea and you want to learn more about tea, smash that subscribe button, and let's dive into today's video. All right, to get things started, we need a working definition of what oolong tea even is. The tea plant is one species of plant called Camellia sinensis, and it produces 6 major tea types. The most famous are green tea and black tea, but you also have oolong tea, white tea, yellow tea, and dark tea. 6. These all come from the same leaves of the same species of the same plant. Same plant, same leaves. It's just after you pluck the leaves, what are you doing to those leaves? How are you processing them differently to create one of those 6 major tea types? Okay, so what about the processing makes green tea different from oolong, which is different from black tea? With oolong tea, basically you want to initiate what's called partial oxidation. The easiest metaphor here is when you take a bite out of an apple, that white fleshy core, if you let it sit, it oxidizes, and if you come back half hour later, it's like brownish. So that's called enzymatic browning. And with tea leaves, the leaves are green when you pluck them. That's not oxidized, that has not been enzymatically browned at all. And then if you let that enzymatic browning happen all the way, then you have black tea. So black tea is just green tea that was allowed to oxidize and enzymatically brown for several hours on end. Oolong tea is just a halfway oxidized tea. So halfway along the way from green tea to black tea, you stop the oxidation. That is oolong tea. Okay, but the important part is that during this oxidation phase, you have relatively small and simple molecules, most commonly EGCG, starting to link together and form larger conglomerate structures that transform the color and flavor of the tea. With heavy oxidation, you might have 5 or more of these EGCG molecules all smashed and mashed together. And that's what you commonly see with black tea or white pu'er. These are heavily oxidized teas. But right in the middle, right halfway along, the journey of going from a monomer to one of these large, big black tea conglomerates, you have oolong tea polyphenols. And so what that looks like is basically just 2. And the molecule that we're talking about in this video is just 2 EGCG molecules, and they've just started oxidizing. And right after the first hydrogen atoms have been removed from the EGCG. Just as a reminder, oxidation can be the addition of oxygen or the loss of hydrogen. So right at that beginning stage of oxidation, you have basically these 2 EGCG molecules reaching out and just clasping their little hands together at this one junction point right here. 2 identical flavin backbones from oolong tea production. Hence, we have the molecule that we're talking about, oolonghomobisflavin. It is basically the first molecule formed when polyphenol oxidation kicks off during oolong tea processing. So really, in a way, this molecule kind of embodies the idea of oolong tea, which is partial oxidation. Because when you continue oxidizing, you no longer have these oolonghomobisflavins, because then they continue to merge and polymerize and mash into other molecules and form these larger conglomerate structures. So you only have them at this early to midway stage of polyphenol oxidation. So that is why they are oolong tea specific. And now we are going to dive into what 30 years of research has reported about the biological effects of this oolonghomobisflavin molecule. The first study on this molecule comes in 93. Great year. A lot of legends were born in that year. In 93, they discovered that oolonghomobisflavin has the ability to mildly inhibit mitochondrial complex 1. It causes a mild stress to the mitochondria. That might sound bad. Why are we stressing the mitochondria? Leave the mitochondria alone. The key is mild and reversible. This mild inhibition triggers mitohormesis, a fancy term for beneficial stress of the mitochondria. When mitochondria face small temporary stress, they adapt, strengthening antioxidant defenses and boosting long-term resilience. And that's actually the same logic behind why exercise is healthy, through short-term stresses to the energy production systems. So this little T molecule mimics the beneficial stress that makes cells tougher. At the time, this was groundbreaking because polyphenols weren't yet recognized as bioregulators, and this is one of the first natural examples of mitohormetic signaling ever documented. By 2005, oolonghomobisflavins had turned heads for a very different reason: their effect on fat absorption. Some researchers in Japan, they test the ability of oolonghomobisflavin to inhibit lipase. Lipase is the enzyme in our digestive tract that allows us to absorb fat from the food that we consume. It's different now, but in the pre-GLP era, weight loss strategies often focused on inhibiting digestive enzymes like lipase and glucosidase. They compared the lipase inhibition activities of a range of Tea-derived polyphenols. IC50 is just the amount of the polyphenol needed to inhibit the lipase enzyme by 50%. So EGCG required a concentration of 0.35 micromolar, while oolonghomobisflavin outperformed every other T polyphenol tested, requiring just 0.048 micromolar. That's 7x stronger of an inhibitor of lipase than EGCG, which is interesting because oolonghomobisflavin is just two EGCG molecules put together, essentially. So that is what we call synergy. It is an effect greater than the sum of its parts. Now, the world allows over a decade to pass without a single new oolonghomobisflavin experiment to be published, which is a tragedy for mankind. But in 2017, a study reignites interest in this oolong tea polyphenol. This time, the focus was on cardiovascular health. Researchers found that oolonghomobisflavins protect LDL, that's the quote-unquote bad cholesterol particles, from oxidation. Because in reality, prior to getting oxidized, these LDL molecules don't actually cause any harm. And the oxidation of this quote-unquote bad cholesterol is actually the key intermediary step that mediates its harmful effects on the body. So the study, they found that the presence of this oolong tea polyphenol significantly reduced how much the LDL gets oxidized. And they were able to measure the structures on the LDL. These are signature structures that are signs of oxidation, right? Because when oxidation happens, it's physically changing the conformation of the outside of that molecule. So there was much less of that. And what that did is that it maintained the heparin binding activity of the LDL. And the heparin binding activity just refers to the ability of that LDL to be latched onto and taken away and cleared out of the artery. You have these great systems that go around looking for LDLs or lipoproteins embedded in the artery, and our job is to scour them, latch onto them, cling onto them, and clear them out. And that binding activity reduces, it goes away when you oxidize the particle because the oxidation changes the shape of the molecule. So oolonghomobisflavin reduced the oxidation and maintained the heparin binding activity of the LDL particle. Thereby, henceforth, ipso facto, the atherosclerotic process was reduced. That's what they proposed, that's what they showed, and that's a very cool thing. All right, so now we are cruising into the 2020s, which, as we all remember, was just such a fun time in history. And we actually have a study coming out. A group of Indian scientists want to see which molecules from tea might be able to bind to and block the SARS-CoV-2 main protease, Mpro. So that's the machinery the virus needs to replicate. Basically, if you can bind to it, let's say the virus is here doing its stupid thing, and then you just bind to it really tightly, it like can't really move anymore, and that's sufficient to stop it from replicating. They tested 65 T molecules, and among all the compounds, oolonghomobisflavin A stood out. So here you can see the top 3 performing T molecules compared to 3 synthetic pharmaceutical antiviral drugs that were already being tested and used at that time. So oolonghomobisflavin showed stronger binding energy than all of the other 64 Tea-derived compounds tested, and it was the only T compound to outperform all 3 synthetic drugs. So in silico, in the computer modeling software they used, this molecule was able to form this incredible web of hydrogen bonds with crucial amino acids of the coronavirus, right at the enzyme's catalytic heart. And if those bonds held true in living systems, they would jam the viral replication process more effectively than synthetic antivirals. Now in 2023 and 2024, we enter a really exciting phase about the role of this polyphenol in oncology. It's 2 articles, but it's one team out of Korea. This is really, really cool what they did. So they discovered that the oolonghomobisflavin attaches and binds to a specific receptor called the 67-laminin receptor. 67LR is what they called it. And this is a receptor that's overexpressed on cancer cells. So if you look at a cancer cell, it's going to have a ton of these receptors. A normal cell, a healthy cell, doesn't have many at all of this receptor. Oolonghomobisflavin binds to this 67LR. And so in the first study, they used melanoma cells. So these are skin cancer cells. They've observed binding. They saw that it did it, and it resulted in this very long signaling cascade. This guy sends a message to this guy, to this guy, to this guy. The net result was less melanoma growth, which is already pretty cool. But that's kind of where they ended things on that first paper. But, that opens up a whole million other questions. Does it work on other cancer cells? Let's follow up with more studies. And that's exactly what they did. So basically, in order for the oolonghomobisflavin to inhibit cancer cell growth, it needs to pass through these various signaling molecules. And a key one is this one right here, and it needs to go up. The problem is that there's this other enzyme called PDE5 that continually breaks this one down. So when that happens, it kind of blunts the whole signal from the oolonghomobisflavin all the way down to the cancer cell. But if you can block this PDE5 enzyme, you can allow this molecule to continually rise and increase and amplify the cell death signal all the way down to the cancer cell. What they did is that they combined the application of the oolong polyphenol with a molecule called diallyl disulfide, or DADS. And this is a sulfur compound from garlic that inhibits PDE5 and therefore allows the cGMP to continue climbing and strengthens that self-destruct signal that the oolong T polyphenol sends to the cancer cell. So in this second study, they used leukemia, and they combined oolonghomobisflavin B with the DADS from garlic. And sure enough, that self-destruct signal intensified significantly. Cancer cells self-destructed while normal cells remained unharmed. And that is true synergy. And this study gives us the biological basis for a brand new tea food pairing that I had never before considered. That is raw garlic and oolong tea. Let's give this a try. Ow. Well, if you enjoyed this video on oolonghomobisflavins and you want to dive deeper into the world of oolong tea, I have a deep dive on oolong tea processing for you right here. And if you want to dive deeper into the whole world of tea in general, the 6 major tea types and everything else, an 8-chapter, 8-video masterclass on tea with chapter 1 I got for you right here. Until the next one, stay healthy, stay positive, and keep sipping tea. One love. I'm crying. I'm literally crying.